right, we've hit the top of the hour here. So we're going to start off with a little bit of housekeeping and things as people are still signing into the program here. But thank you all for joining us today. My name is Sean Maurer. Joining me today is Daniel Held with Woodard Quran. I'm going to talk a little bit about some energy efficiency projects they did at Carlinville, give you all some insight into some infield practice. And I'm going to be going over just what we've seen through our program with the public water infrastructure assessments for options for energy efficiency to hopefully spur some ideas for facilities and get you going. If you do have questions as we're going through our presentation, feel free to use the Q&A window. Should be in the center toolbar of the screen. If you pull that up and enter your questions there, make sure we don't lose them in the chat. If you do put them in the chat, I do have Cassie Carroll watching the chat for us to hopefully pull some of those questions out and make sure we answer everything as they come in. Um, So diving into today, a little bit of background about who we are here at the Smart Energy Design Assistance Center. We are an applied research program at the University of Illinois. We assist buildings and communities in achieving energy efficiency, saving money, and becoming more sustainable, with the overall goal for our program to reduce the energy footprint of Illinois. So we thank everyone for tuning in today and learning a bit more about what we do. As part of our program, we do research, we do on-site energy assessments, uh, educational opportunities, such as what we do here, and we advocate for a sustainable future. A little bit about our partnership here with the PWI Energy Assessment Program. It is a partnership between CDAC, the Illinois EPA Energy Office, and ISTC, the Illinois Sustainable Technology Center, to provide no-cost energy assessments to publicly owned water and wastewater facilities throughout Illinois, to help reduce the cost of treating and providing water and wastewater to your communities. As part of the program, we do offer a comprehensive energy assessment report where we detail existing conditions at the plant, provide an initial benchmark for your facilities. We go over upgrades and potential improvements for the facility, the cost of those upgrades, estimated payback periods, and any applicable incentives or funding opportunities to help push those projects forward. Also, as part of the program and what you're experiencing today with our webinar, we do provide operator continuing education. Again, as I noted at the start, CEUs will be provided by the end of the week for you. So thank you for attending today. We will get that information out to you to provide those continuing education credits. If you are interested in an energy assessment, you can apply for it at our website, www.smartenergy.illinois.edu/water. So we'd like to touch on why plants might want to consider having an energy assessment. If you're in an older existing plant or you've never had an assessment before, we can help operators identify missed opportunities for not only new equipment and energy efficiency upgrades, but also potential tweaks to their existing process and things that can help improve um, energy efficiency, operational efficiency, and treatment quality. We can help you plan for capital improvements at your site. If you're getting ready to do an upgrade or working with an engineering firm, we can help provide some ideas and opportunities that might be available to you and uncover what's possible for your facility. We also provide third-party support for operators' ideas. We come out to the site when we're doing our site assessment. We ask questions about what you'd like to see at your facility, any issues you're dealing with. We try to incorporate those things into our report so that it's tuned to what you need and can help drive forward your projects as well. What about if you have a brand new facility or it was recently upgraded, so you've already added a bunch of energy efficiency features, or you think your plant has been improved significantly already? We always find more ways to improve. For any project, there's always a limited budget. Things get cut out, left on the table to fit within the budget for the project. So there's always something that's left to improve. So we can help plan for long-term planning and improvements out into the future. We can also help plan for improved resiliency, net zero planning, and things like that. And there's always new technologies and processes in development being researched. We try to keep our ear to the ground for those technologies and provide those to you as a component of our assessments. And as always, we're always connecting facilities to funding potentials, grant opportunities, and utility incentives. So step one, to apply for an assessment, go to our website, smartenergy.illinois.edu/water, and fill out our pre-application form. Just verifies that you qualify for our program. You have to be located in Illinois and be publicly owned. You have to provide permission for CDAC and ISTC engineers to come out to your site and gather information about your facility. You do have to be willing to share facility information and utilities. So we're going to gather your DMR reports, utility information that helps us benchmark your facility. We're going to gather information about existing equipment, motor nameplates, things like that, to help us determine where your potential savings opportunities are. And we do finally share that report with the Illinois EPA Office of Energy. It is a non-regulatory report to track the effectiveness of our program. So be aware that we do share that report with Illinois EPA, but it's not going to trigger any kind of regulatory requirements or anything for you. Step two is the data collection process. Once you fill out that application form, provide those permissions for us, then we are going to gather that facility information, utility information, and DMRs. If you are a water plant as well, you do have to provide the monthly operating reports to us, as there isn't a centralized database for us to pull that from. But we do try to make this data collection step as easy as possible. It is the most common hangup in trying to bring plants into the program, because a lot of times the plant doesn't have direct access to their bills. There's the city clerk or someone at the municipal level that has access to that information they have to work through. So we do try to either directly connect with that person, um, or work through this information on phone calls or gather it on site if we have to. But we'll work with you to make this data gathering process as easy and as smooth as possible, so that we can get out to your site and give you the quality assessment that you're looking for. And then the third step is, once we have all that information, we've got some initial benchmarking ready. We'll schedule a site visit. When we come out to the site, we're going to spend a couple hours out there with you going through the facility. We'll go over that initial benchmarking and what information we've gathered from that as far as what we expect to find in terms of operation. And we'll talk to you about how the plant is working, where you've got issues, where you'd like to see improvements. We'll talk about how you're working at the plant, settings, set points, all that kind of stuff to help inform our energy assessment. So getting into today, our webinar, we're talking about energy efficiency opportunities specifically for activated sludge plants. Coming up next month, we'll be talking about lagoon facilities and energy efficiency opportunities for them as well. But one of the big things for most activated sludge plants is your aeration system. 50% or more of the energy intensity going into the plant typically goes towards aeration systems. So one of the common upgrades that we've seen at almost most of the plants we go to is at least partial conversion from coarse bubble to fine bubble aeration, if not in every basin, in most of the aeration basins. Theoretically, the savings for this can be up to 70%, just because you're getting much greater surface area contact between the oxygen in the air bubbles and the water. But that is limited by alpha factor, beta factors, other quality of the mixed liquor in your aeration basins. So we typically see with a coarse bubble system, standard oxygen transfer rates somewhere around 2, increasing to about 6.5 with fine bubble systems. Your actual energy savings based on what your previous controls were. Again, quality of the mixed liquor and other factors at the plant, your savings can vary anywhere between 10 to 50%. So really key to come out to the site, work with an engineer to understand the quality of the water, the aeration configuration in your basins. All those things have an impact on how much you can potentially save by switching to a fine bubble aeration system. Um, Aeration controls is the next thing that we'll kind of dig into. Control can be as simple as a timer on your uh, blower system, or if you've got rotors for an oxidation ditch, or you could get into as complex a control as ammonia-based aeration controls, combined with DO controls, things like that, to really fine-tune the process to your loads. Um, the more control you add, the more potential for savings that we generally see. Going from a simple control, you might see savings in the 10 to 20% range. As you get more and more advanced, especially if you're starting from having no control, your aeration's running 24/7, then that savings potential gets higher and higher, um, up to, again, somewhere around 50% of your aeration energy. Um, what we do find for a lot of plants is there is a balance that needs to be struck between the savings potential and the upkeep and maintenance for that aeration system. So, a smaller plant that doesn't have a large budget might go with a simpler system, and that's effective for them. Where a larger plant has more opportunity, more funding, to install a higher control system, with more advanced control options. So, um, what we've seen very commonly at most places is they can get away with simple DO control as a cost-effective option that pays back within a couple of years. 2 to 3 years is usually what we see for that. Um, for larger facilities with large aeration systems, we can see more advanced controls pay back in a similar time frame. Something else, a lot of plants are working towards nutrient removal. Hitting tighter and tighter stringency on nutrient removal for nitrogen and phosphorus at facilities. And so we'll look at whether there's opportunities to incorporate energy savings into the potential for nutrient removal control. A lot of extended aeration plants can convert a portion of their basins into an anoxic zone, so you can partition off either the head of the aeration basin or a separate aeration basin as an anoxic treatment zone to help with denitrification. And because you're reducing the amount of aeration going into that basin, you're also cutting down your overall energy consumption for the plant. Um, so proportional to the amount of aeration you're turning off to turn on to create that anoxic zone is generally linearly proportional to your aeration energy savings. So if you've got three basins, you turn one of them into an anoxic basin and the other two remain as aeration, you could generally see somewhere around 30% savings in your aeration energy. Um, the other thing, if you're using chemicals to balance pH, by doing denitrification, you return some of that alkalinity back into the basin, reducing that need for chemicals. So there's additional savings outside of just the energy consumption alone. We've also seen aeration cycling as a common savings method, particularly with oxidation ditches. We can run the rotors for a little bit, then turn them off for a period of time, turn them back on after the system's gone to an anoxic condition. Um, and that can give you a little bit of benefit for that nutrient removal in the process without having to do advanced aeration controls, invest in VFDs, things like that. Um, but that is an option for some of the smaller plants that we run across that don't have the ability to invest in high capital projects, is just looking at whether you can cycle your aeration off to create a temporary anoxic condition, turn it back on, go back to your fully aerated condition, um, and balance out nutrients that way. Um, Another thing that we try to recommend for facilities, if you've got um, an even distribution of aeration throughout your aeration basins, what we tend to find is that can create some control issues and balancing issues with aeration basins, particularly where you've got some of the more advanced controls already in place, where you're trying to track nitrogen in those basins. Um, because as loading shifts throughout the plant, you don't necessarily always need the entirety of the aeration basin for aeration. Um, Towards the end of the process, that load is taken care of. You don't need as much aeration at the end of a treatment basin as you do at the head of it. What this leads to is, your DO might be at set point at the head of the basin, but as you get to the end, now you're over aerating the process. Um, for basins that have zone-based controls, this can lead to fluctuation of the control valves in the aeration system and difficulty in balancing airflow through the diffuser system. Tapering that aeration system can help with balancing those airflows by ensuring that you have um, consistent airflow to the diffusers so that they're all getting the same volume of air through each individual head of the diffuser. It makes balancing valves to each header a lot easier. Um, but that tapers down the aeration as you need it through the process so that you have a lot less fluctuation in control valves, manual balancing if you're doing that. Um, this makes that process a lot easier to do and provides a little bit of energy savings as well because you're not providing full aeration throughout the entire basin. Uh, the next most important thing, once you've got aeration itself dialed in, um, is then having proper control of the blower system providing air to that system. A lot of times we go out to plants, every plant is sized for future growth of some amount. And so the equipment is generally going to be larger in capacity than what your current needs actually are. And so having the ability to stage equipment or dial it back with a VFD is often very important in order to maintain overall efficiency. Um, when we look at facilities that we've been to, the ones with greater potential savings are generally the ones that have fewer large pieces of equipment to meet their loads, and the ones that already have good control are ones that have multiple smaller units that provide more staging capacity. So for initial capital cost savings, what we find is a lot of times there's your two primary blowers in place. It gives you some staging capability with a third one as a backup system, is probably the most common that we've run across. But we have been out to plants. You get a picture in the bottom right here where they had 5 blowers out there for their digesters and they had separate blower system. There were 5 blowers for their aeration system. That gave them a lot of staging capability because they had a lot of change variability in their flows due to inflow and infiltration. Um, so just something to be aware of. If you put a VFD on a blower, generally that's going to give you a 2-to-1 turn down capability for that individual blower. If you have 2 blowers that works together, give you a 4-to-1 overall turn down range. Um, Best practices recommend that you should have a 6-to-1 to an 8-to-1 turn down capacity in order to meet varying loads throughout the day, particularly as you have diurnal load peaks. You're going to need quite a bit of turn down to hit those lower levels and optimize your efficiency. That 8-to-1 guarantees that. 6-to-1 gets you pretty close to that. If you've got a 4-to-1 turn down ratio um, through one of these 2+1 aeration setups, you're going to probably over aerate your system when you're in those lower loads. Um, so again, if you put a VFD on a blower, most blower systems, that turn down range is going to be somewhere around 2-to-1. For a well-designed blower, properly designed blower system, you might get a 3-to-1 turn down with a VFD on a single blower. And then you want to be able to stage multiple blowers to get you to that 6-to-1 to 8-to-1 turn down ratio. Um, Also, the more blowers you have, the more redundancy you're going to build into your system. So if you have a 2+1 system and you happen to have an issue with 2 of them for some reason, unfortunate as that may be, now you've got a problem. But if you've got multiple blower systems, 4 or 5 of them, it's less likely that you're going to have a critical issue where you're not able to provide adequate aeration. Um, Looking at high efficiency blower upgrades for plants. Improving the blower efficiency itself is a relatively small impact on aeration energy consumption over controlling the actual aeration capacity to the process. Um, but as that blower system is going to be there for many, many years, it has a much bigger impact over the long term in how much energy you're spending on your aeration system. So ensuring your blowers are properly sized to your loads, have adequate control and appropriate turn down is going to get you the biggest impact. but then making sure that those blowers are as efficient as possible and working at their most efficient point is an important consideration. We do know turbo blowers have the highest peak efficiencies, but that type of blower system maintains that efficiency at that design point. As you start to move off that design point, you start to lose efficiency on that system. Centrifugal blowers are a little bit better overall in their turndown range at maintaining efficiency. But as you get below a certain range, they are going to start to lose efficiency. And you do have a limitation on your pressure requirements for how much you can turn down those blower systems. Positive displacement have the lowest peak efficiency, but they can maintain efficiency over the widest operating range. It's almost constant the entire operating range of that blower system. Um, so sometimes what we run across at plants is a hybrid blower package system. They might have a turbo blower or a centrifugal blower that's handling peak loads when they're at their peak design condition. And then as they get to lower loads, they may go to a positive displacement system because it's more efficient at those lower loads than one of those centrifugal or turbo blower systems. Um, because they will, again, lose efficiency as they drift away from that design operating point. So then getting into pumping systems and what we find there, every wastewater plant's got to move water through the system. Um, not Most plants are designed initially to have gravity flow. So you got an initial lift into the plant and then gravity flow through the system. But as we've been incorporating more and more nutrient removal, that introduces recycle flows where you've got to return some flow back up to the head of the plant or back up to the start of an aeration basin. So there's a lot of pumping involved. And as we noted earlier, most plants are sized for future growth. So those pumps are going to be oversized for most typical conditions. Um, Again, this is very similar to what we talked about with blowers. VFDs can help a lot to adjust pumps to varying flow demands. With programming, you can avoid some issues we've run into. I know we recommend VFDs a lot for lift stations, and we've had a couple communities remove those VFDs because um, they would slow down the impeller too much and it would increase the amount of clogs they were getting in the system. And so it was increasing the number of times they're having to go out and do maintenance work on those lift stations. But with VFDs, you can introduce programming to them where they can automatically clear clogs. They can either start with an initial reverse flow to clear clogs into it and then kick into forward flow um, to draw any materials through the pump. They can have a minimum safe starting speed to ensure that there's enough suction to pull materials through so that they don't bind on the impeller. So there's different control methodologies for VFDs that can help ensure that they're not a maintenance headache. But you do have to work with your designer to make sure that they're aware of any issues um, and plan for those in the programming and control of those VFDs. Typical savings for individual pumps, again, depends on what the current system is, but that can range from 10 to 50%, depending on the conditions, how much the pump is oversized, um, cycling rates, runtime hours throughout the year, um, all have an impact on what that potential savings can be. Right sizing the pumps, again, kind of touching back to the same issues as we have with blowers, depending on conditions. VFDs may not have sufficient turn down for low flows, or the turn down can cause clogging and ragging issues. So you have a limitation on how low you can go in that speed. Um, Adding in a smaller pump, being able to stage multiple pumps can help address some of those issues. Where the VFD isn't taking on all the work and can provide some additional potential savings. So making sure that those pumping systems are sized correctly. If you do have a plant that's sized for future growth, that you have a couple of pumps sized for what you currently need, and then a couple of pumps for what that future growth potential is going to be, is an optimal way to design around efficiency, although it does introduce some additional capital costs at the start of the project. Selecting pumps for VFD application can be a little tricky. Definitely work with your applications engineer to figure out whether a VFD is going to be a good application or not. What you're seeing on the screen here was a case study example we did looking at a set of lift station pumps where VFD wasn't a good option. You can see the blue dotted line is the pump's full speed operation. It's already far to the left of the best efficiency point for this pump, where if you put a VFD on that, you're going to be working, this system would have been working outside the recommended operating range for this pump, where you're going to have increased vibration, increased wear and tear on that pump system. So VFD just wasn't a good option here. It was best, if they maintain this specific pump, to go remain with on-off control of that air lift station. So when looking at VFDs, definitely make sure you're looking at the existing pump and the existing operation curve for the application. Um, Ideally, you want the operating point for your pump to be a little to the right of the best efficiency point if you're going to add a VFD. That way, as you slow the pump down, you actually increase the efficiency and maintain it at a higher point for longer. It gives you more operating range and control for that pump system. So this is something that we can help with in the analysis and looking at, as long as we have the information on the pump curve, and we can estimate kind of what your system curve looks like. Um, so again, VFDs can be very helpful, but only if they're applied in the right conditions. We have seen in situations where VFD is applied and it either can't be reduced in speed, or it cause additional maintenance issues because the entire system wasn't looked at properly. Next thing that we'll get into in your site, we've hit the large energy consumers with pumps and aeration. What's left is your facilities and the site conditions. So looking at lighting, HVAC, building insulation levels, things like that. We're going to try to see if there's opportunities for improvements there that are cost effective. Lighting is one of the most common cost-effective things that we've seen. Most of the implementation we have to the program, 80% of the implementation projects have included some kind of LED lighting upgrade. Um, so incentives are usually pretty good for lighting, that we have rapid to instantaneous paybacks. We've had a couple of Ameren projects and ComEd projects that have fully funded the lighting upgrade. So there's no remaining capital cost to the plant after the incentives. Um, But for the purposes of planning a project, we like to target hard to replace lighting first. So if there's lighting over a basin where you've got to set up scaffolding or a lift to access it, um, outdoor lighting up on light poles, things like that, where you need a ladder or something to access that lighting system. Those are good options for replacing with LEDs, because one, it's going to save you the energy on the LED itself, 50 to 80% of the lighting energy, depending on the LED lighting upgrade you do. And it's going to save you on the labor and equipment rentals and things like that to replace that lighting. Um, Another area is vapor tight fixtures. It takes a little bit of time to open those fixtures up, access those bulbs, swap them out. So if you can get it an LED that's a long life bulb that will probably last for the majority of most people's work careers at a site, um, then that's an excellent upgrade that's going to save you a lot of labor. Um, the other thing is to target highest run times. Outdoor lighting's on 50% of the year, whenever it's dark out, plus a little bit extra for cloudy, rainy days. So those are an excellent opportunity. They're going to have the best paybacks. Consistently occupied spaces like the central admin office, things like that, where the lights are on every time someone's there, those are going to give you the greatest payback. Um, Places where we tend to find that paybacks aren't as great, or um, lighting for plants that aren't occupied consistently. This happens a lot with smaller communities where they don't have an operator dedicated to the site. He's only there off and on through the day, and then he's doing other work throughout the city um, or the municipality that he works in. So there is some variability in the potential for lighting savings, but there's always the additional benefits of the labor savings for changing out those lights. There's the waste hauling of the old bulbs and stuff, as those bulbs need to be recycled for fluorescent lighting and things like that. So these things are all factors that play into a lighting upgrade. But as we go through a report, we'll try to break out where you have good opportunities for lighting savings, and where maybe you can delay until that lighting fails and then upgrade it with an LED. High efficiency HVAC systems are another thing. So many sites that we go to, we see traditional unit heaters in spaces, either electric unit heaters or gas unit heaters. And a lot of times there are heat pumps available that can reduce the energy consumption of those by um, significant amounts, 50% to 75%. You know, air source heat pumps are 3 to 4 times more efficient than um, electric unit heaters or gas unit heaters. If you can do a water source system, we've seen a couple of plants that have tied in a heat exchanger to their effluent stream to pull heat energy out of the effluent and use that in a water source heat pump system. Those can be 5 to 6 times more efficient than traditional heat sources. Um, for plants and communities that are interested in moving towards um, resilient net zero facilities, electrifying the plants is one of the big steps towards that because gas systems, it's harder to get renewable energy credits for gas heating. With electric systems, all you got to do is tie into either on-site renewables or you could do community renewable energy. There's multiple ways to tie into renewable electric. Um, so a lot of times when we're going out to plants, we're recommending high efficiency air source heat pumps for like electrical rooms um, and garages, things like that, where we typically see those older unit heaters that are really not very efficient. Um, so with careful design of a water source heat pump system, I know we've run into a couple of plants that have been very happy with them. We've run into a couple of plants that have had issues with them where the heat exchangers clog and has created more maintenance issues for them, and they weren't very happy with it. But if you do design it well, you can put it in the effluent system where there's the least risk, or tie it into your non-potable water system. Um, that reduces the risks for clogging of the heat exchanger system. Um, that's where those water source systems are going to be most efficient and least impactful to your overall maintenance. Um, but even mini split heat pump systems can provide effective heating for 90% of the year. A lot of these systems now are coming out with low ambient units that can work down. They'll maintain 80% or more of their design heating capacity at temperatures down to negative 20 degrees. So if you have an HVAC guy that's telling you, heat pumps don't work well in this climate, there are options that do. And they minimize the need for backup electric heating so that you don't have to invest as much in electric upgrades to the plant. Um, so there are those opportunities. Another thing we run across is ventilation controls for plants that have anaerobic digesters, that have hydrogen sulfide high content in their influent streams. We tend to see these used for monitoring and safety alarming. Um, but there's also an opportunity to tie them into ventilation system for control and reduce how much you're ventilating a space. Um, Mainly, we see this for like hydrogen sulfide ventilation purposes. You're detecting really the oxygen concentration in the air, making sure it's at a safe level. Um, but we also see for a couple of sites that we've been to have used these um, for hazardous space alarming and detection, as long as it's not an NFPA 820 space. Um, there's that explosion risk consideration for ventilation that has minimum ventilation requirements to meet different classifications for NFPA 820. If a space could be Division 2, um, for that space classification, intermittent ventilation is acceptable. You can use these types of sensors to minimize how much ventilation energy is applied to those spaces. It saves you on the actual ventilation fan's energy. It saves you on the heating of makeup air for that space or the cooling of that space if it's also cooled. Um, there's multiple different ways and sensor pairings you can use to control those spaces and help minimize that ventilation energy because that can be a quite significant energy cost. Lastly, we'll look at renewable options. This is particularly important as US EPA is planning to release a NOFO for wastewater treatment plants sometime soon, probably at the start of the next year, to fund renewable energy projects, focusing on the ability for plants to be resilient in the case of power outages and self-supply their own power. Combined heat and power, where plants have anaerobic digestion, is a very, very common system. Most common, we see CHP engines that are reciprocating gas engines. Um, they're very common. Most people are familiar with how a reciprocating engine works. It's just like your car. So maintenance is relatively easy in terms of training. Although we do find reciprocating engines are probably the most maintenance intensive of the CHP engine systems. Um, there are other options out there, and you should look into whether those options are maybe a better fit for your plant. Um, Reciprocating engines, again, they can be average in terms of efficiency. Um, Most of the times we see them applied, with proper design, they can have the highest efficiency available in terms of total energy conversion for heat and for electric. Um, they're very familiar again, which makes maintenance training relatively easy. Um, and the cost of finding replacement parts is generally easier as they're not specialized. And they handle load variations really well. They're able to ramp up and ramp down, but they are very maintenance intensive. They do have to go through periodic full shutdown, tear down, rebuild process. Other options include micro turbines. They're good for smaller generator capacity if you've got a smaller plant. Um, Average overall efficiency, relatively low maintenance on them. However, the parts are custom, so there is a cost premium because this is an engineered turbine that's part of that generation system. The parts for that can be expensive when they do need to be replaced. So even though maintenance is less on these, it can be a little bit more of a premium on the parts when they are needed. They're best for consistent loading. They don't handle load variations well, so storage is important to buffer swings in gas production. Gas turbines are similar to the micro turbine system. They're best at a peak load design. They have the highest available capacities. So if you have a fairly large plant, maybe a gas turbine is an option for you. Um, Although a lot of wastewater treatment plants won't maintain consistent enough loading to justify a gas turbine. Maintenance is comparable to the reciprocating engine, except for the turbine, again, which is an engineered part. So if there's an issue with that, there is a cost premium for that turbine. And another final option is fuel cells. It's a different type of technology, has very, very high electrical conversion efficiency, but it's a lower overall thermal efficiency as you're not doing a lot of energy recovery off of those. Fuel cells are best for consistent loading and may be an option where emissions from combustion are a concern because fuel cells convert the biogas into a hydrogen fuel cell rather than burning that gas. So there's no emissions from a fuel cell system. They're also very quiet, which may be beneficial if you're in an urban or suburban environment where you've got residential areas right up against the plant. Um, Again, it's a specialized technology, so there's a higher initial cost and ongoing maintenance cost um, due to the rarity of these systems. They're not very common, um, but there are those additional benefits as far as emissions and things that might be a consideration for your plant. And they are generally less maintenance intensive than some of the other options because they aren't combusting a material. Another renewable option, solar photovoltaics. Many plants have flat roof buildings or open ground that can support the installation of solar panels. Um, there's multiple options now. In the past, PPAs were probably the most common, a power purchase agreement. Excuse me. It's offloaded the maintenance to a third party for those array systems. And essentially, you negotiated an electric rate that you would pay for the power generated by that system. And with net metering, that would balance out payments that you were paying to your standard utility. Um, the reason that was pretty common option was previously it was more difficult for public entities, government entities to gain the tax credit for solar arrays. That was changed with the the Inflation Reduction Act, where now direct purchase and installation of solar panels, government entities can apply for that 30% tax credit. So that means you can directly retain the solar energy credits, and those are also can be sold at market for um, to offset the cost of installing renewables. Um, And another thing to be aware of is that net metering for Ameren is sunsetting at the end of the year. We haven't determined yet whether ComEd is going to do the same or not. Um, that means that that rate that you're getting back from the utility isn't going to be one for one like it is now with net metering. It's going to be a market rate. So the savings potential from installing solar is going to be a little bit less, where maybe a PPA isn't going to be as viable anymore. Direct purchase might be the option that you go for there because you do have now access directly to those tax credits. Um, when installing solar PV, one of the things we recommend is considering pollinator gardens underneath those panels. Reduces your maintenance as you don't have to mow that down as frequently as if you just had grass, or if you had gravel under there, it's not as appealing. Um, it's a way to advertise to the community that you're being sustainable with practices at the facility. Another option for solar is floating solar. If you've got a lagoon or a basin that you can float these panels on, it does improve their overall efficiency by keeping the panels cooler. It keeps them cleaner as they're not exposed to windblown dust and things like they are on the ground or on a roof. Um, and since they're floating out there on the basin, it can help control algae, duckweed, things like that. If you've got flow balancing basins or secondary lagoons or overflow basins for your facility, it might be a good option to look into. You don't have to purchase additional ground or find land to install these on. That could be a potential option. Last thing, we've had a couple of plants interested in installing outfall turbines to generate electric power on water flowing out of the plant and into a receiving stream. There are low head generator turbines that are available where they can generate power from variable flows. Um, for these to really be cost effective, higher flows are needed for more and more reduced head to get significant power generation. So if you've got, you generally need an elevation of 3 to 15 feet. If you're on the lower end of that, you'll want higher flows. If you're on the higher end of that, you can maybe sustain a little bit lower flow through the system and make it cost effective. Minimum flow rates for these generators is generally somewhere around 400 gallons per minute required. Um, but if you've already got like a cascade outfall to your plant, you've got enough available head there to install a turbine as a potential option for supplemental power generation at your plant. Um, we've had a couple of plants ask about these. One, I think, was moving forward with engineering and bid discussion about it. The other was determined not to be a viable site, but it is an option to look into. So with that, I'll turn it over to Daniel with Woodard Curran. If you want to give a little bit of background about the plant you've worked with and some of the efficiency projects that they worked on out there, I'll turn it over to you. You are muted.
All right. Thanks, Sean. Appreciate that. Yes, Sean, what he said there was correct. I do work for Woodard and Curran. We're a party that we're a privately owned company that works with municipalities to run their water and wastewater facilities. We have plants across the country. We're about 1,100 people. About 600 of those are engineers. 400 or so are are on the O&M side, and we're into a lot of different projects. You know, collection of garbage at airports, a lot of water, a lot of wastewater facilities, that kind of thing. So with the Carlinville project here, so we took over there in August of 2018. And back at that time, their wastewater treatment plant was having a lot of problems. The plant generally treats about 1 million gallons a day. It can treat up to 3.75 million, full treatment. After that, it will bypass up to 18 million. But with that bypass, it should go through primary clarification, then chlorination, and then you take the chlorine out of it before it's discharged. That was not happening, so we had lots of work to do at that facility because they were in jeopardy of being in big trouble with the state of Illinois for being out of compliance every month and all that kind of stuff. So uh, when we were there, we started working on that project, and then we were looking at the electrical bills, and this opportunity came about. So we reached out to uh, the folks there, and they initially came out and did the original report, I believe, in like 2019. Now, not long after that, we ran into COVID, and so there were some delays there, and the city was unsure where their funding was going to be. So there was some delay there, but eventually we got the project underway in 2021. What the report recommended was is that you have an opportunity there with lighting, as you had mentioned, uh, with a lot of plants, and with the aeration. And as it turns out, the aeration, was really going to be a benefit to us, but because of our desire to replace the existing plant, we waited on the lighting. So what we ended up with was we ended up with a project where they were going to go in and they were going to put in 3 VFDs on our blowers, and they were also going to mount a control DO meters in the aeration basin. And what that was going to do is, we're going to set a area that we want the DO to be. And so that's going to be monitored, and then the VFDs were going to be controlled based on what the DO needs were. Now for Carlinville, we have 3 things that kind of manipulate what happens with our wastewater coming in. Number one is about 40% of the collection system is combined sewers. So we're on an average day, our flow might be 1 million. If we get a 2.5 inch rain in Carlinville, our flow might move to more than 18 million. So in the beginning, that water, the low, or what's coming in there, the loading is going to be much greater than it will be 12 hours after that. That's going to be mainly rainwater. We also have a large dairy operation in town, and once in a while they will discharge stuff that will be high in loading and require additional air. And we also have a college in Blackburn College in town there. And depending on what they're doing over there, that can have an impact on us also. So the VFDs, as I said, were going to help us. So we moved forward with that, and we got the approval from Ameren on 3/18/2001. And the initial cost estimate for the overall project was about $50,000. The incentive that Ameren provided for the project was about 30,000, somewhere around in there. And so in working through all this with the Sustainable Technology Center and with Ameren, we ended up accomplishing the project at a cost to Carlinville at about $20,000, something to that effect. We were reviewing the results, Sean and I were the other day, and it looks like that we're saving somewhere around, I'm going to say in a range of around of about $6,500 a month, a year. I'm sorry, $6,500 a year. So you can see on the payback on that, for the city, is additional, or basically about a 4 to 5 year time frame. So the project was it was a very good deal for us. All the folks that were involved were very easy to work with. I will say the toughest part of the project is getting your information, for your utility bills, to the folks who need it, so they can analyze it and, take a look at, what the cost benefit is and all that stuff. And so we accomplished that project, I'm going to say sometime in the summer of 2021. And, it was a great deal for the city, saved them a lot of money.
One of the things I wanted to touch on as we were looking at that analysis was the change in the utility rates. So we were looking at what we had originally estimated in the report for savings, which what you're actually getting with the implementation of the project.
Right. Right. You do have some variables there. So if if your loading changes, and in our case, the loading has changed some since 2001, that you can see or you can see where that would manipulate what the savings would be. There are all kinds of variables there, to how much rain we get, that year, what's going on with Prairie Farms, what's going on, the dairy that's in town there, what's going on with the college. When COVID hit, and everybody was doing everything remote, the campus was, pretty much only had about 20% of the student body that it would normally have. So that accounts for some of that loading, I would think, you know, just that element of it.
Also, your utility rates climbed up. You were paying, when we started the assessment report, it was about, remember, it was 2.5 cents a kilowatt hour. Now it's up to 44 cents a kilowatt hour. So your actual payback has improved.
Right. I think everybody probably experienced that. We all
Yeah.
know these utilities are not, what they were 5 years ago. And I don't think anybody sees us, bringing those back down, regardless of whether we drill baby drill or not,
Yeah.
to be honest with you.
Well, thank you for that overview, Daniel. The um, I was going to ask about the aeration control system with the existing blowers. Are you typically using two of the blowers and one's on standby, or do those vary
Uh,
off and on much?
Usually, the way they used to run it, and this was really inefficient, for the city, which was, they would have a blower going at all times,
Mhm.
because you're always going to have wastewater coming in. So they always had one going. There would be mornings when they would come in and the DO would be very low because the loading increased, for one reason or another. And so then they would kick the second blower on to bring the aeration back up. Then you could have a rain event, or perhaps the loading goes back down. So then you might go in and the DO would be way high in the basin
Mhm.
because the loading isn't near as much. And so the way we have this set now, I believe, is that you'll have a blower running. If both blowers shut off and the DO starts to drop and it drops below a certain level, you get an alarm, obviously, because a blower should be running and it's not. And then the DO information is sent into uh, you know, into the CPU, and and it kind of controls that. So if the DO drops to a certain level, it'll kick on the second blower. If it drops below a certain level, further, then generally we'll get an alarm, because we really don't have very often have a situation where we have all three blowers running at the same time.
Okay, great. Thank you for that background. We did have a couple of questions come into the chat. One person had asked, back when I was talking about anoxic zones and extended aeration basins, whether it's safe to do that if your system has primary clarifiers. Um, I've seen it done at plants with primary clarifiers. Usually what you're doing with the primary clarifiers, you're reducing some of that initial BOD loading that's coming into the plant, and sending that into waste sludge. Um, but that shouldn't impact um, the capacity in your aeration basin, in terms of um, your aeration need for the loading that was in that basin. Um, so when you're looking at whether you can add an anoxic zone or not, the main thing that you're looking for is if you're treating all of your BOD loading before you've reached the end of that basin. So if you've got a DO set point that you're maintaining, and it's pretty consistent through part of the basin, and then it starts to climb towards the end, it's generally an indication that you're have met your treatment need, and now you're going into kind of excess aeration towards the end of the basin. That can indicate whether you had the potential to turn off a portion of that basin to create an anoxic zone for denitrification. So you're more looking at the loading in the aeration basin itself, um, and where you're hitting that point, whether you've got excess capacity in that extended aeration basin, to make that decision. Um, Scanning through the chat here to see if we've had another question come in. You had mentioned that Carlinville was looking at a future project to move the plant and convert to more gravity flow.
Well, Sean, do you have an overhead of the plant by chance? Got to put you on the spot here, but if you could throw it up on the screen there.
I can see if I
Um,
can find one.
yep.
if you want to
Okay,
discuss a
I
little
can
bit
kind
as
of
I go
walk, I
through
can
it.
kind of
Yeah.
walk through it anyway. So, with the plant, where it's at now, the plant opened in like 1951. So it's well past its design lifetime. And with the, ever-changing requirements from the IEPA and the tightening of the requirements on phosphorus and that kind of thing, uh, you know, the the city has decided that they want to build a new wastewater treatment plant. So what the plan is now is we're going to have the water come into the plant at the headworks just like it does now. But we want to pump it up the hill from there. And right next to the road, right above the little red sewage plant, dot there, that's where the mechanical screen is, where you had your arrow right there. And we want to redo that facility down there, and then we're going to pump it up the hill towards where it actually says Mayo Street there, and you see this old driveway. So there was a house up on top of that hill that was sort of abandoned and had asbestos in it and all that stuff. So we worked with another grant through the Housing Development Authority, and we had that house and garage and all that stuff out there removed. It had a little asbestos in it, so we had to have the asbestos removed. And so it is now as you see it, which is you have the driveway there, but there's nothing up on the facilities. We left the tree line in there to the north of the property so that the folks who live north of there, which you can just barely see at the top of the picture, their view out their window towards the south will be the same. And by moving the plant up to the top of the hill, in the existing plant now we have somewhere around 15 pumps and motors that are running at the plant at different times, so you have the redundancy with the plants and everything like that. With this new plant, we hope to be able to, we'll have the plants down low there, but we would be reducing that number to like three, so there'll be a lot of energy savings in that. If we were going to be there in a longer time frame, we would probably move forward with the lighting project for sure. So it's a good project, but the payoff for that is, a little longer. Then we
Mhm.
hope that the plant will be in operation.
Okay, well, great. Well, thank you, Daniel, for that overview. I don't see any other questions have come into the chat, and we are coming up on time here. So I'd like to thank everyone for joining us today. Daniel, any concluding thoughts for the audience?
If you got an existing plant that's got a little age to it, and it does not cost you a thing to have those folks to come out and take a look at it and sort of do a review of your location and make suggestions. And from there, if you don't think the payoff is going to be there, or you don't think the city fathers will go for it, that kind of stuff, you can kind of end it right there. But if there is opportunity for energy savings there, I would jump on that because you know like I said, we started down there in 2019, and right now we're just to the point where we're getting a facility plan to the Illinois EPA for them to approve and perhaps fund a portion of that project. Then you still have to go through the actual engineering to design it, and then you have to let it, and you have to get a contractor, and you have to get all those things. So where you're thinking, well, we're probably going to build a new plant. You're probably 10 years anyway from building it by the time you jump through all those hoops and everything. So I would definitely check into that. Danny Marsh was the guy who came down and did our energy assessment. Great to work with. We were working with the folks from Ameren. We were working with the folks at Illinois Electric down in the St. Louis area. They were the ones that actually did the work. Very easy, not a lot of time. We didn't have to put a lot of time into it or anything like that, and the payoff has been fantastic. So it's a great program.
Great. Well, thank you.
You're
Well,
welcome.
thank you all for joining us today. Again, if you are interested in an assessment, you can reach out to us at cdac-info@illinois.edu or apply directly at smartenergy.illinois.edu/water. And we look forward to hearing from you all soon. Thank you all for joining us today.